So let's see what happens when you try to iterate MapReduce based matrix vector multiplication. First time, of course, you have to read the matrix A and read the vector X in parallel by all the mappers. Then the intermediate stage, rather after the first MapReduce phase, you write the Y prime, and then you have to read the Y primes, and then at the end you'll write the Y's all in parallel because every reducer computes a few rows of the final Y. But now you have to once again read the matrix A and the Y's that you've written in the previous iteration, write Y prime, write Y again, and continuously read A again and read Y. So there are two places where you're reading things again and again. One is here you're writing Y prime and reading Y prime again, which you can potentially avoid by pipelining using technique like Hadoop and other implementations, where you can pipeline the writes and the reads from the writes of one reducer to the reads of the next mapper in the next phase. But we still have the problem of having to read A again. Notice MapReduce does not have any memory. The basic assumption is that the data is just too large, it will never fit in memory, and so you essentially have to read A again and again. But suppose it did fit in memory. MapReduce still has no memory, so it can't really remember A between iterations. The mappers don't know what they're going to get next time. It's a random order of reads every time. And so MapReduce iterations are inherently inefficient in this regard, that if A is really a huge matrix, lots and lots of edges, or rather lots and lots of entries, then it's just going to have to read it again and again and again. So this is definitely a problem, and there is a way around it, which is essentially leads us to Pregel. Let's look at this same matrix vector operation now as a graph operation. What do I mean by that? Think of this matrix as defining edges in a graph. So for example, the fact that you have the first node, which is the first column, or has an edge which leaves it and goes to the second vertex. And similarly, there's an edge going from the second vertex to the first vertex. So read each column as the edges that go out of, say, the first vertex, and read each row as the edges that come in to the first vertex, for example. So here you have -1, which is just the vertex itself, diagonals all -1, and it says there's an edge which comes in from 2, and there's an edge which goes out from 1. Now let's take a look at 3. It has two edges going out, 1 to 4, which is this entry, and 1 to 2, which is this entry. And it has one edge coming in from 4, which is this edge over here. And you can verify that this particular matrix, which is called the adjacency matrix of this graph, represents all the edges in this graph. So the diagonal elements represent just the vertex, and we treat them as -1 for reasons which we won't go into in this course. And the off-diagonal entries represent edges in this graph. Now what about the vector x itself? Well, we assume each vertex holds a value which is nothing but the element of the x vector in the appropriate position corresponding to that vertex. So the vector 1, 2, 3, 4 is distributed across the vertices of the graph as just 1, 2, 3, 4, which one element per vertex. Now let's think of the matrix vector multiplication as being done in parallel by each vertex in the following way. Each vertex sends its value out along all its outward edges. So 2 sends its value to these two vertices, and 1 sends it to this one, and so on. And then all the vertices start receiving the values that were sent in this step, and they receive values from all their neighbors on incoming edges. And finally, the vertex replaces its value by the sum of everything it receives minus the value that it originally had, which is essentially, as you can easily see, it performs exactly the matrix vector multiplication that was going on. Now, the interesting part of this is, it's very parallel in the sense that as long as you have many processors and each processor has bunches of vertices, you can really do a lot of these operations in parallel. The only caveat is that you have to exchange messages, so you have to try to make sure that the vertices are placed so that they don't have to exchange messages between different processors too often, and that's a challenge, as we'll come to that in a short while. But the really important part of this is that it's easy to iterate. Once the graph structure has been loaded into all the processors so that every vertex knows its outgoing edges, then you don't need to load this matrix structure again. You can just keep iterating again and again, repeating the matrix vector products as is often required in many applications. Unlike MapReduce, where you have to load A continuously every iteration, A is loaded once, since all A is just a vertex and its connections to neighbors, that's all. So the caveat, of course, is that if the number of edges is so huge that even using all the memory of all the processors that you have, you can't load it, then you can't do this. So the caveat for Pregel, this is the Pregel model actually, we'll come to that formally in a minute. The caveat is that you need to have enough memory to load the entire graph in order for this to work.